Hello class, we're going to look at some applications of derivatives and the circular functions, and we're going to have this as a video and not cover it so much in class. One thing we need to think about is how do we work with different differentiation techniques involving circular functions. And what's interesting is what is the derivative of tan of x. If we know rules for derivative of cos is minus sine, and derivative of a sine is a cos, how can we draw on that to work out the derivative of tan? Okay, so let's work through this. Now if we've done this, for those students that have done this in specialist maths, okay, then you've got a heads up, you've seen this before. So this video is aimed for, in particular, our other maths method students that haven't studied specialist maths. Okay, so let's go. First, let's think about what is tan of x. Tan of x can be expressed in terms of two other type functions. We have sine of x divide cos of x. Okay, that is a fundamental rule for the tan of x function. Now, from that, I get a rational function. It's like a division. I have to use my quotient rule when I'm differentiating. So the quotient rule says that the derivative of any function that looks like u over v, then it is v times u dash minus u times v dash over v squared. So I need to identify what am I going to use for v and u, and then v dash and u dash. So let's break it up. Let's u being the top function, which is the sine of x, and that means u dash would have to be derivative of sine is cos, following the rule. And my v, which is the part on the bottom, the cos of x. And so the derivative of the v function, derivative of cos, is a minus sine. Alrighty. Now let's put it all together into the rule for the quotient. So I now have the derivative of the tangent function, which is what I've got, my y. Well, that is the v times u dash. So we take it here, put it all over a bracket, cos of x times u dash, which is also another cos of x. And then I subtract u times v dash, sine of x times v dash is minus sine of x. Okay, all over v squared. Now my v squared is cos. All squared. Okay. Now, what does that give us? With these circular functions, it's good to be able to simplify them, particularly when we're squaring. So cos times cos, same thing. So I can write it as cos squared of x, and that's the notation we can use. We can put the square just above here in the cos. Okay. Now we're subtracting sine of x times negative sine of x, subtracting a negative value in this multiplication, overall positive. So add sine squared of x all over cos squared of x. Good. Well, here we go. Is that as simple as we can get it, though? That's the question. Doesn't look very straightforward, but then again, I'm going to draw on an idea about sine and cos terms and come up with an equivalent value for this one. Okay? Now, there's something called a trigonometric identity, Okay, and there's special rules that tell you how an expression of trig functions, how they might simplify to something like a numerical value. So one trig identity says that cos squared of x plus sine squared of x is equal to 1. Okay? Now, interesting reason why that comes about is by drawing on Pythagoras and trigonometric ratios at the same time. It all comes down into a right angle triangle. So let's say here's my right angle triangle for some angle. Now, if I have a hypotenuse, the longest length of 1, and my adjacent length of a right angle triangle is equivalent to the hypotenuse multiplied by cos theta, and we need to think about SOHCAHTOA, and that the cos of the angle is the adjacent side, which is this side, I divide the hypotenuse, and the opposite side of the triangle is equivalent to sine of theta for a hypotenuse of 1. Okay, now if I draw on Pythagoras Theorem, Pythagoras Theorem says, well, the longest side of the triangle, the hypotenuse side, is labelled C, and then C squared is equal to A squared plus B squared. From that, drawing on the right sides of the triangle, I have 1 is equal to cos squared theta plus sine squared theta. Okay? And so be it. There's our trig identity. It's a very useful expression to use when simplifying circular function expressions. So, if cos squared x plus sine squared x is equal to 1, I end up with a small simple expression of 1 over cos squared x. And that's a nice function to be the derivative of tan of x. Okay? Believe it or not, this guy is called something else. 1 over cos, 1 over sine, and 1 over tan. They themselves have their own circular function names. This is a sec squared of x rule. Okay? 1 over tan is called a cot of x, and 1 over sine is a cosec of x. And if you're interested in learning about them a little bit more, you're welcome to delve into some trigonometric rules and expressions on the internet. It's a good extension of your learning to help build your skills for math methods exams. So, working with our circular functions is important. Being able to apply our differentiation techniques in different scenarios is important, and it needs practicing. So I'd like you to think about this set of questions here. Alright, for each of the following, find f of dash at pi. So f dash is your derivative, and we have to evaluate derivative at pi, x equals pi. Okay? Start with something like the first one. So, let's have a look at that one. There's our function. Now, we want to evaluate this gradient function at pi. So we have to find that derivative function first. df of x dx. Okay, now what kind of function is it? Again, it's a quotient. We have to use our quotient rule. So in finding this, doing this derivative, we've got to break it up in terms of our u and our v. So we've got let u equals the top expression, 2x, And so u dash, its derivative, is equal to 2. That part's easy. And then v is the bottom, cos of x. And so v dash, its derivative of cos is, you guessed it, minus sine. All right, put it all together. Our derivative now is our applying the rule. Do you remember what it is? I do off the top of my head. V times u dash. So I'll have a 2 cos in the first part. Then we subtract u multiplied by v dash. This cross business. U times v dash. So I'll have a 2x times negative sine of x. And when we do our substitution for the first time, it's good to just lay it out like this with brackets over v squared, which is cos squared of x. Oh, well, this is an interesting part. I've got 1 over cos squared term popping up again. So that, remember from the previous question, is equivalent to a sec squared. Let's simplify the top. I will have now 2 cos x plus, subtracting a negative becomes an addition, 2x times sine of x over cos squared x. Okay, now I want to be able to clean this up a little bit. So I've got some common factors here, 2. Let's take that out. And I've got a cos of x plus x times sine of x. All in the numerator. And now I'm going to multiply it by 1 over cos squared of x, which is simply a sec squared of x. Okay, so one little thing, little identity there that we can keep is a sec function, circular function, is 1 over cos of x. Okay, excellent. So another application of differentiation, important technique to be able to do. Last step, we need to evaluate this now. What is this result? What's going to be the rate of change at x equals pi? So for that, f dash of pi equals 2 lots of cos of pi plus pi times sine of pi multiplied by sec squared of pi. Okay, now don't be scared about this bit. It's really straightforward. I need to know my exact values of circular functions, don't I? I need to have that table of sine, cos, tan, and all my known angles available to me. It's got to be up in here. I have to know them. I need to know them for the exam. What is cos of pi? Wesley? Yep, you got it. -1. That's right. That is -1 plus pi times, what is sine of pi? Jaleel? 0. Good job. So it's times by 0. And then multiplied by sec squared of pi. Now, sec squared of pi. Sec squared of pi. How do we think about such a problem? Well, let's come back to the meaning of sec of x. 1 over cos of x. So if I'm evaluating this part here, I need to think about evaluating 1 over cos of x, and then all squared. So I know cos of pi is -1. Now if I divide -1 by 1 over -1, that's still -1, and if I square that number, it becomes +1. So multiplied by 1. Very easy. Told you. And simply, when I expand all that out, I'll have 2 times -1, which would be -2. Okay? Excellent. Practice, practice, practice. That's all it takes. All right, please find the time. Let's have a look at a slightly more complicated problem involving differentiation with circular functions. We're just going to do part A to start off with, and then you can continue on and do part 2 in the next video. The diagram shows a 5-meter pole leaning against the vertical wall. The lower end of the pole moves away from the wall at a constant speed m. So we've got a problem where it's starting to slip at a constant speed of a meters per second. Well, we don't know what that value is, but we can think about it as that moves across, then this end of the pole is going to move down the wall. Interesting problem. Now, we need to think about some related rates of change. Find the instant that the foot of the pole is 3 meters from the wall. 3 meters from the wall. Okay, so the foot of the pole must be 3 meters away from the wall. We've got some length away from the wall here, from there to there. We're going to call that x. Okay? Which that's going to now represent the distance of the foot of the pole away from the wall. So it's good to label that down. X is distance of foot of pole away from wall. All right. Now, so we've got one unknown quantity labeled, and we called it x. What about as this pole slides down, we've got the height from the top here that it's going to slide down the wall. So let's give that another quantity label. Let's call that h. Okay. So one thing we can see already in this relationship, as x is going to increase, the height is going to come down and get smaller and smaller down to the ground. It's also going to decrease. So I wonder in what way that will occur. One thing I notice is that I have like a right angle triangle problem occurring, where my hypotenuse is 5. This length is for some changing angle. This length of the triangle is h, height, and this one is x. Right? So I can see straight away that 5 squared is h squared plus x squared using Pythagoras. Okay. Now, transposing that, I'm going to have my height will then be the square root of 5 squared, which is 25, minus x squared. Okay, and I've got a relationship now. As x increases, I've got a rule that's going to work out what's the corresponding height that the pole is up the wall. So I'm interested, reading the question carefully, we want to find, for the instant that the foot of the pole is 3 meters away from the wall, so when x is 3, the speed at which the top of the pole is descending. The speed at which the top of the pole is descending. Interesting. So the speed is... Go! Alright, so something about speed. We have we can think of speed as distance divided by time, and where the speed of what we're interested in is the height that it falls down the wall. Okay, so the top of the pole descending is a speed decreasing in this manner. Let's see that if this is what we're after, dH dt, and we have a function of h with respect to x, then we have to note down via chain rule how do all these rates are going to interact, how they're going to connect. So I'm after a dH dt. Now, since I've got a function of h with respect to x, I need to know what is that rate of change. And then for that to be equivalent to dH dt, I must know my dx dt, the rate at which the foot of the pole moving away from the wall is having. So if we know dx dt, then I can work out dH dt, that speed, that rate of change. And we've got information about how quickly this foot of the pole is moving away from the wall. So we're told that it moves at a constant speed of a meters per second, some constant quantity. So let's use on that fact, where dx dt is equal to a meters per second, and I must work out what is the rate of change of the height with respect to the distance away from the wall, x. So dH dx is equal to the derivative of this function. Now, this is chain rule, again, application. And chain rule says that if I've got an inside function, I must get that derivative, which is negative 2x. Derivative of the 25 is 0, and then the derivative of the second term is negative 2x there. So that's the first part, multiplied by the outside part, the derivative of the square root of u, which is the substituted pronumeral for the inside. That is now 1 over 2 square root of pronumeral u, which is 25 minus x squared. Okay, so we're just applying the steps of chain rule to acquire this expression. Simply, our 2 divide 2 will cancel out, so we won't have that factor of 2 there. Over square root of 25 minus x squared. Okay, so what is now this rate at the instant that the foot of the pole is at 3 meters? So when x is equal to negative 3. So that equals 3. I'll have dH dt will equal to the negative 3, so substitute 3 into x here, over 25 minus 3 squared, which is 9, negative 3 over the square root of 16, which is negative 3 on 4. Okay? Meters per second. Alright, now I'm going to use this rate of dH dx at x equals 3 meters away from the wall, and we're going to work out what is now the rate of descension of the pole as it falls down. So therefore dH dt is dH dx, which is negative 3 on 4 multiplied by dx dt, which is just a. Negative 3a on 4 meters per second. Okay? So, essentially saying, if the foot of the ladder moves away from the wall at some given speed, then the top of the ladder is going to descend from the wall at 3/4 of this speed. Interesting. Okay? I'll let you think about part B by yourself. You're after the rate at which the radian measure of the angle defined by the pole and the horizontal between the bottom of the pole and the wall is changing. That seems a little tricky. But we are interested in the rate at which the radiant measure changes. So this theta is what we're thinking about, and we want what is the rate of change of theta. So let's just note down that d theta dt is what we're after. And maybe we can consider what is what theta depends on. What do you think theta depends on? Maybe the quantity of x. As x increases, what happens to theta? Does that increase or decrease? So we might need to know what is the rate at which theta changes with respect to x. And to make the chain rule consistent, we then also must need to know the rate at which x changes with time, which is a quantity we know and we've worked out previously. A meters per second. Alright, so it's a little hint on how to tackle that problem. Have a go, try B, and if you have any questions, please ask.